Uh, Hello dear students, in today's class we are going to prove few properties that hold in a ring. The first property that we are going to prove is a dot 0 is actually equal to 0. Later on we will prove that a into minus b is equal to minus ab and finally we will prove a into b minus c is actually equal to ab minus ac. Let us jump into proving property number a. So proof a. Now remember, in this property this 0 is actually nothing but additive identity. Now first of all let us recall properties of rings because that are essential in order to prove the properties that hold in a ring, right? This A, B and C. So the first property of a ring that we already know is plus is commutative, then we know plus is associative, then identity exists in a ring. This is the additive identity and we are calling it as 0. Remember that this additive identity is unique in a ring. Next property is inverse, existence of inverse with respect to addition. It says that take any element of a ring we are calling it as A, then there exists minus A belongs to R such that A plus minus A is equal to 0. Remember, take any element of a ring R, A plus minus A is always going to be equal to 0. Then multiplication is associative, existence of unity is there, and the last is multiplication distributes over addition. Now let us begin the proof. Note that what is the existence of identity property saying? It is saying that A plus 0 is equal to A for all A belongs to R. Now this 0 is actually element of R itself, so this property will also hold for 0, right? So in particular if we put A is equal to 0, so what we are going to get? A is equal to 0, right? So 0 plus 0 will be equal to 0. That is what we have. So 0 plus 0 is actually equal to 0. Now to prove A dot 0 is equal to 0, now we will consider the left hand side. So I will say consider LHS. So what is my LHS here? A dot 0 which is equal to, but I already have the value of 0 from here, right? Let us call it as 1. So this is equal to A after putting the value of 0 as 0 plus 0. This is using 1. Now we are going to use the property P7, that is multiplication distributes over addition. So this will be equal to what? This will be A0, A dot 0 plus dot stands for multiplication in a ring, A dot 0. So what we actually have here is A dot 0 is equal to A dot 0 plus A dot 0. Now since this A dot 0 is an element of a ring, remember what I told you, for all elements in a ring A plus 0 is equal to A. Now since this A dot 0 is also an element of a ring, so this property will hold for A dot 0 also. So what will be my value of A dot 0? A dot 0 will be equal to A dot 0 plus 0, right? We are just replacing A by A dot 0. So this implies this is A dot 0 plus 0 is actually equal to A dot 0 plus A dot 0. So now this is using P1, not P1, P3, right? Now we are going to use a famous law that we have already studied in group theory, and that is nothing but cancellation law, isn't it? So we can cancel out this a dot 0 from both sides. Therefore what we will get, 0 is equal to a dot 0, and that is exactly what we wanted to prove. But remember, whatever cancellation law we use in rings, that is with respect to addition only. We cannot use cancellation law with respect to multiplication. What is the meaning? Ki a plus b is equal to a plus c will imply b is equal to c in rings, because cancellation law with respect to addition will hold. Now why this happens? Because this first 4 properties actually proves that ring is a group with respect to addition, right? And we know the cancellation law holds in a group, right? But we are not sure whether ring is a group with respect to multiplication. We are not sure about that, isn't it? Because the existence of inverse property is not included here. Thus, whenever we are having AB is equal to AC, that may not imply B is equal to C with respect to multiplication. Just we have to remember this while using cancellation laws in ring theory. Now let us prove the second property, that is a proof of B. Now here we have to show that A into minus B is actually equal to minus AB for every AB belongs to R. Actually I forgot to tell you one thing in the last proof. Remember this A is an element of a ring, right? And it is an arbitrary element, because as you see in the question, this property actually holds for any element of the ring. So just what I will write here, let A belongs to R, and then we will consider LHS. Okay, remember it is just an arbitrary element of a ring. Now let us move towards the property B, the proof of property B actually. Now what is existence of inverse property saying? You take any element of a ring A plus minus A is always equal to 0. This minus A is actually called as the additive inverse of A, and remember, additive inverse in a ring is also unique. Now what is the meaning of that? Let us say A is the element of a ring, and if you have A plus B is equal to 0, and you also have A plus C is equal to 0, right? So it implies that B is also a inverse of A and C is also inverse of A. But what does uniqueness imply? Uniqueness actually implies that B is actually equal to C, isn't it? Because there exists a unique element and we are calling it as minus A actually. A plus minus A is equal to 0. This is the only one, right? Now here we have to prove that A multiplied by minus B is actually equal to minus AB, and this we have to prove for every AB belongs to R. So just let me pick 2 elements of ring first of all. So I'll say let AB belongs to R be any elements. Now as I already told you, A plus minus A is always equal to 0, right? Minus A is the additive inverse of A. Now here, since this A and B are elements of ring, so their multiplication, that is AB, is also a element of a ring. Now since AB is an element of a ring, now we are going to use this property. So what will happen is, first of all let us write AB is an element of R, and therefore AB plus this minus AB will be actually equal to 0. Okay, yeah, like this, minus AB is actually equal to 0. Let us call it as some 2. Now we are going to observe one beautiful notion. just note that what is the value of AB plus A into minus B. Let us just solve it and let us see what we get here. Now, as one can easily observe, here we are having A, here we are having A, right? And just see this multiplication distributes over addition property. So we are going to use this property in this direction. As one can see, if we are having A's on the left, that can be taken out, isn't it? So this A can be pulled out. So A, what will be left inside the bracket? B plus minus B, which is actually equal to, now again, as I mentioned earlier, in a ring, A plus minus A is always equal to 0, right? A is an element of a ring, isn't it? Now here B is also an element of ring, so what will be B plus minus B? That will be 0. So simply use that property. So this will be equal to A multiplied by 0. This is using P4. But what is A into 0? What we have proved in part A of this theorem, A multiplied by the additive identity is always equal to the additive identity, that is 0. So this will be equal to 0. So what we have proved here, therefore AB plus A multiplied by minus B is actually equal to 0. Let us call it as 3. Now as I mentioned earlier, key additive inverse is always unique. I mean, if A plus B is 0 and A plus C is equal to 0, and what does it imply? This B and C are exactly the same, isn't it? Now what is happening from equations 2 and 3? So if you observe carefully, AB is an element, right? This AB is an element. So AB plus this is equal to 0 and AB plus this is also equal to 0. But due to uniqueness of the inverse property, what will happen? This A into minus B will be exactly equal to what? Minus AB, and that is what we want to prove in our property. So what I will say here, this implies A into minus B is actually equal to minus AB. Okay, this is using 2, 3 and what we have used, uniqueness of inverse. Now let us move towards proving the part C. Part C is the easiest one. Again we have to prove this result for 3 elements of a ring, any 3 elements of a ring. This is not set of real numbers, this is simply R. So let us take 3 elements of a ring, arbitrary elements. I will say let ABC belongs to R be any elements, and just I will consider the left hand side of what we want to prove. So A into B minus C. Simple. How can we do it? This is equal to A into, how can you write B minus C? This can be written as B plus minus C, as simple as that, which is equal to, now we are going to use the property multiplication distributes over addition. So this is A into B plus A into minus C. But what we have proved in part B, this A into minus B is actually equal to minus AB. So this A into minus C, which is nothing but minus AC. So this is equal to AB minus AC. So just mentioning the reasons, what we have used here, we have used P7, and what we have used here, part B of our theorem, and that is exactly what we wanted to prove, and that is our left hand side, and this was our LHS. So that's all about this theorem. Thank you.